Well, students, we are discussing open domain methods for approximating an isolated root of a nonlinear equation. In this section, we have covered secant method and Newton-Raphson method. In this lecture, we will study another method called fixed point iteration method. This method is quite commonly used in theoretical studies. However, they are also well suited for numerical computation. In this method, we have to first rewrite our given equation f of x equal to 0 in an equivalent form x equal to g of x in such a way that a root of the equation f of x equal to 0 is equivalent to a fixed point of the function g. So for instance, let us take f of x is equal to x square minus x minus 2. Then we are interested in solving the polynomial equation x square minus x minus 2 equal to 0. Clearly, this equation can be rewritten as x is equal to x square minus 2, in which case our g will happen to be x square minus 2, right? Not only this, our given equation can also be written as x equal to root x plus 2, in which case our g of x is root x plus 2. In fact, there are many other ways that we can write this equation in an equivalent form x equal to g of x. Okay, once we choose one of these equations, then we have to set an iterative sequence. How to do that? Well, once you choose a g from your original equation f of x equal to 0, then the idea goes more or less the same as the Jacobi method. You first start a x naught arbitrarily and find g of x naught and call it as x1. And once you have x1, you find g of x1, and that will give you x2 and so on. In general, once you know xn, you can generate the next iteration xn plus 1 by taking xn plus 1 equal to g of xn. The function g is called the iterative function of this iterative sequence. Note that the iterative function is not unique for a given equation f of x equal to 0. We have seen this in the previous example where we have at least generated 3 iterative functions for the given equation, right? Let us formally write the algorithm. The first step is to decide what g you want to take, that is the iterative function that you want to take to generate your iterative sequence, and also you have to choose an initial guess x naught. So the inputs of this method are the iterative function and an initial guess. Once you have these two information, then you can start generating your iterative sequence using this formula. For instance, if your equation is x square minus x minus 2 equal to 0, like what is given in the previous example, and you decided to choose g of x is equal to x square minus 2, then you can set up a iterative sequence using this function g. Why? Because x equal to g of x will happen to be x equal to x square minus 2, and that will give you x square minus x minus 2 equal to 0, and therefore a root of this equation is equivalent to a fixed point of the function g, right? If you recall, a fixed point of a function g is the point such that g of x is equal to x. That is, if your function g is represented by this graph y is equal to g of x, and we know that this line is nothing but y equal to x. So a fixed point of the function g is nothing but the point of intersection of the line y equal to x and the graph of the function y equal to g of x, right? So this is a fixed point of the function g. So the first idea is to write your given equation in an equivalent form like this, and then take that g and generate your sequence. Like in this case, xn plus 1 will be xn square minus 2 for n equal to 0, 1, 2, and so on. And to start this iteration, you need to know what is x naught. So you will choose your x naught and then you will start generating the sequence. So this is how the method goes. You would have clearly seen that the crucial step in this method is to choose your iterative function. If you choose a bad function, then you may land up with either a diverging sequence xn, or your sequence xn itself may not be well defined after a finite term. These are the two ways that your method can fail to capture the root of your equation, right? So therefore, your choice of g should be in such a way that it should not land up with any one of these two situations. On the other hand, your g should be chosen in such a way that the sequence generated using this g should be well defined, and also it should be a convergent sequence. And the last and not the least is that the limit of this convergent sequence should be a fixed point of your function g, right? So that is what is meant by good. Let me repeat once again. If we say that we are having a good iterative function, it means what? For the given starting point x naught, the successive approximation xn given by xn plus 1 equal to g of xn should be well defined. That is, you should be able to calculate this number xn plus 1. Then the sequence thus generated should converge to some point, say xi, and finally that point xi should be a fixed point of the function g that you have chosen, right? It means what? Xi should be equal to g of xi. Of course, that xi should also be a root of your equation, but that should not be a problem because you have rewritten your equation f of x equal to 0 in the equivalent form x equal to g of x. Therefore, if you make sure that xi is a fixed point of g, it will automatically be a root of your original equation f of x equal to 0. Now the question is how to choose this g, because we have seen that given a nonlinear equation f of x equal to 0, we may have many options for g. Therefore, it's not very clear which of these options can be chosen in order to fulfill all these desired properties, right? Let us take one by one and see how we have to choose g in order to fulfill the properties. Let us take the first property. For the given starting point x naught, your sequence xn should be well defined, right? That is the first and foremost condition that we need. Let us take an example to see when your sequence may not be defined at all. Let us take this equation x square minus x equal to 0. Well, you can rewrite this equation as either x equal to root x or x equal to minus root x, and other ways also. But let us take one of these two and see how we can go wrong. Say, for instance, if you take g of x equal to minus root x, then, well, this will be equivalent to x equal to minus root x. That is not a problem, but can we generate an iterative sequence using this g is the question. Well, suppose I take x naught is equal to 1, then my x1 will be minus root 1, which is minus 1, and then my x2 will be minus root minus 1, which is not a real number, right? Therefore, this is trivially a bad choice for my iterative function. Now the question is how to obtain an iterative function so that the sequence xn is well defined. Look at this equation. We have rewritten our equation f of x equal to 0 in this equivalent form, right? Therefore, we are going to work with this equation now. Therefore, for every given x, g of x should be defined, right? Now, when can this happen? Well, suppose g is defined on an interval a b to say r, then what it means? It means for every x in AB, g of x is defined, right? And in particular, we want that value to be also finite because we are later going to obtain the terms of our iterative sequence using the value of g at the previous iteration. Therefore, at every iteration xn, g of xn should be finite. Therefore, what we want is that our g should be chosen in such a way that its value should again be in the domain of g. You take g such that g of x also belongs to AB. Then what happens? You take a x, you get a g of x, and now you apply again g, it will be again well defined, and you will have g of x. Such a function is called a self map. So we will impose this condition that g is a self map, in which case we are sure that our sequence is well defined. It means what? Whenever you choose a x between a and b and apply g on it, since g is a self map, its value will also be in the interval a to b. And since g is a self map, therefore g of x also belongs to AB. And hence, when you go to compute g of x, it is well defined because g of x is sitting in the domain of g. And in that way, all the members of our sequence will be well defined. So let us impose this condition. When we choose our g, we have to make sure that g is a self map in an interval in which there is at least one root for your equation. Therefore, we have finished our first property by imposing the condition that g is a self map. Let us go to the third property and see how g should be chosen in order to fulfill the third property, and then we will come to the second property because third is very easy to do. So let us finish it first. What is the third property? The third property says that the limit of your sequence should be a fixed point of your function g. Remember, we have bypassed the second property and came to third property. When you are in third property, we are assuming that the sequence is converging and then talk about its limit. That is why I told limit xi. Okay. So assume that sequence xn generated by xn plus 1 equal to g of x n is a convergent sequence, and say it converges to xi, right? Now we have to put an assumption on g such that xi is equal to g of xi. Now the question is, what is that assumption that I have to put on g so that this condition holds, provided if my sequence xn is converged? You can clearly see that limit n tends to infinity xn is your xi, right? And now using this, I can write this as limit n tends to infinity g of xn minus 1. And now I want it to be equal to g of xi, right? When can that happen? Well, if I can push this limit into the function like this, then I am through, because then I will get g of xi, right? But when can I push the limit inside the function g? Well, that needs g to be continuous, right? Again, I'll tell you that if I assume g to be continuous, then whenever my sequence xn converges to a limit, say x star, then I can write x star equal to limit n tends to infinity xn, and that is equal to limit n tends to infinity g of xn minus 1, because that is how we have defined our sequence. And since g is continuous, I can push the limit into g and get x star to be a fixed point of g, right? So this is very simple to understand. Hence, our assumption 2 on g is that g is a continuous function. So far, what we have learned is, when I go to choose a good iterative function to generate the fixed point iteration of my given nonlinear equation, I have to choose g so that it is a self-map, it is a continuous function. And now one more property we need in order to make sure that the sequence xn is a convergent sequence. Remember, we have just bypassed the property 2 and went to property 3. Now we will go back to property 2 and see what condition that we have to impose on G in order to make our sequence xn a convergent sequence. Let us illustrate the convergence and divergence of fixed point iterative sequences graphically in order to get intuitive idea. Let us first draw the graph of an iterative function g for which the corresponding iterative sequence converges. Let us take the initial guess x naught here, and what is our x1? x1 is going to be g of x naught. Now let us see how to obtain x1 on this graph. Observe that g of x naught is this point, and where does it lie on the y-axis? Well, it lies at this point. On the graph, this is the point x naught comma g of x naught, and from here we have to see where x1 lies. x1 is nothing but the point of intersection of the line y is equal to x and this line of constant y is equal to g of x naught. And precisely this is the point x1 as per our fixed point iteration sequence generated by the iteration function g given by this graph. Now what happened is, we started with the x naught, and that x naught now moved to x1 in this way. Let us indicate this direction by an arrow. And now what is x2? x2 is nothing but g of x1. So first we have to find the value of g at x1, and that is coming here. So this is our x1 comma g of x1. Once you get this, you can see how to obtain x2. For that, first you draw the line y is equal to g of x1, the constant line, and see where it intersects the line y equal to x. So it intersects at this point. Therefore, x1 now move to x2, where x2 is given by this point, right? So from x1 you move to this. So let me put an arrow here. and then we went like this. And now to get x3, you have to catch hold of this point, which is x3 comma g of x3, and then draw the line y equal to g of x3, and then see the point of intersection of this line with the line y equal to x, right? So that will give you x4. So x3 is given by g of x2, and graphically you obtained x3 by first coming from x2 to g of x2, and you caught hold of this point, which is x3 comma g of x3, and from there you go along the line y equal to g of x3 and get the point x4. Right? x4 is given by g of x3, and similarly you will go along this path to get x4 g of x4. Remember, you have to also draw the direction in which you move, and that gives you x5 as this point. So x5 is equal to g of x4. So you came here to get g of x4, and then don't forget to again draw the directions. So once you have this, you got x5, and therefore you can obtain g of x5 here, and then you go along this path, x6, and then g of x6, x7, and like that it goes. Remember, this is your fixed point xi, right? So when you start x naught like this, you see if the graph of the function g is given like this, then your fixed point is actually attracting towards it, right? Generally, this path is called the orbit. You have to also specify the direction in which it moves, and the sequence is getting spiraled and getting attracted to the fixed point. Next, let us take a graphical example where the iterative sequence goes away from the fixed point, unlike in the previous example. Let us consider an iterative function g whose graph looks like this. Just guess what is the key idea that is going in my mind while drawing this graph. As usual, the point of intersection of the graph y equal to g of x and the line y equal to x is a fixed point of the function g, which is given here. And this time, let us take our initial guess naught very close to xi at this location and see what is going to happen. As we know, this is the point x naught comma g of x naught, right? Once we have g of x naught, now we can locate the point x1 by drawing the line y equal to g of x naught and see where it intersects the line y equal to x. Again, once you get x1, you should locate the point x1 comma g of x1 on the graph of the function g of x. Don't forget to put the arrows that defines the orbit actually. Now you move on to locate the next iteration point x2. Similarly, you can get x3 in this way. Again, put the arrows in the direction in which we moved. Then locate the point x3 comma g of x3 on the graph, and then move on to get the point x4. I'm sorry, it didn't come well. Just assume that it's a straight line and go on to locate your x5. Again, put the arrows. This is your x5. And you can keep on going like this. Here you can see that the iteration points are going away from the fixed point, and looks like this sequence is going to diverge, right? In the first example, we say that the sequence is attracted, and in the second example, we say that the sequence is repelled. I hope you would have guessed the idea behind how I drew these two graphs, which made the corresponding iterative sequences attracted and repelled. Yes, the slope of g near the fixed point is the key idea. If the slope of the function g is strictly less than 1, then the corresponding iteration will get attracted. Therefore, we take our assumption 3 as follows. The iteration function g should be differentiable in the interval where g is the self map, and further we should be able to find a constant k which is strictly less than 1, such that mod g dash of x should be less than or equal to k. By this, we will get that mod g dash of x is strictly less than 1 and is away from 1, right? So that is the idea, and this should happen for all x in the interval ab. Such a function is called the contraction map. Let us summarize all the assumptions that we are going to impose on the iterative function. First is that the function g that we choose should be a self map in the interval in which our original equation has a root of our interest. This condition makes our iteration to be well defined. The next condition is the continuity of g, which makes the limit of the sequence to be a fixed point of g, provided the iteration converges. Finally, in order to give the guarantee for the iteration to converge, we have to assume the contraction property of g in the interval ab. Now we are ready to state the convergence theorem for the fixed point iteration method.